Hi, I'm Helen. I'm a postdoc in the Performance and Algorithms Research Group, and today I'm going to be talking about my work on optimizing search layouts in packed memory arrays. This is joint work with Brian Wheatman, Randall Burns, and Aiden Village. The main topic of my presentation today is about dynamic data structures. And one example application for dynamic data structures is in storing and processing dynamic graphs. So like this is an example of a graph. And dynamic graphs appear in computational biology, for example, in modeling protein interactions. And these dynamic applications require data structures that support point operations, such as insertion and finds, as well as range operations, such as scanning through the data. And traditionally, dynamic data structures have been good for one of these types of operations, but not the other one. For example, dynamic arrays are good for range performance, but slow for point operations. And on the other side, trees, which are a classical type of data structure, are good for point operations, but bad for range operations. And we introduced the search-optimized packed memory array, which is a new dynamic data structure that overcomes the trade-off between point and range performance. The search-optimized PMA, or SPMA, is built on the packed memory array data structure, or PMA data structure. PMA is a dynamic array that stores elements in sorted order, and it stores them in one contiguous array. It's suboptimal for point operations, such as find and insert, but it's efficient for scans because the entire thing is one big array, so it's contiguous. And the PMA structure is this array that is logically broken up into chunks. So the actual representation is just one large chunk in memory, but it's logically broken up into pieces. And the way that searches work is doing a binary search on those pieces. And this is some data to summarize the results and show you exactly what I meant by this trade-off. So the x-axis is a bunch of different operation types. A scan is a range operation that reads over all the data. Find and insert are point operations. Find is like check whether an element is in the data structure, and insert is add like some element into the data structure. And its y-axis is normalized performance, and up is good. So we have the PMA, we have a B+ tree, which is a variant of a classical B tree, and we have the SPMA. And the line at 1 is at B trees. So up means that the thing was better than B trees, and below 1 means that the thing was worse than B trees. So like I said, PMAs and SPMAs are good for scans because they're contiguous and they're both better than B trees. PMAs, unfortunately, are worse for find and insert, so both of these are below 1 when compared to B trees, but SPMAs overcome this issue and they're good for both find and insert, so both of these bars are above 1. Yeah, so now I'm going to show you how we got there. And so this is like the main issue with doing PMA searches. So the PMA is stored as one giant contiguous array, and it's broken up into these logical pieces called leaves. And leaves each have a head, which is one element in the beginning that the binary search happens on. And unfortunately, when we do a binary search on these leaf heads, the jumps in the binary search are each far away from each other. So they incur cache misses almost every time we have to jump around in memory. And so the high-level idea of an SPMA is pretty simple, actually. It's just we had these leaves, and each of these leaves have a leaf head. And instead of spreading them out in the array, we're going to move the leaf heads into a separate array and maintain some mapping back into the original PMA. So this idea is actually not super complicated. One natural way of storing the leaf heads is just be in the original order that they came in. So this is like the first leaf head maps to the first leaf and so on. And the reason that this is better is because the number of leaves and therefore the number of leaf heads is much smaller than the total amount of data in your PMA. So co-locating the leaf heads makes this array much smaller and it enables it to fit into parts of the cache hierarchy that the original PMA might not have fit into. So this is a plot to tell you kind of like more concretely what I meant by that. The y-axis is the number of bytes used for the data structure, and the x-axis is the number of elements in the data structure. So expect the amount of space that the thing takes to be greater when you have more elements in it. And indeed, that is what we see. And these horizontal lines are the sizes of L1 and L3, L1, L3, which are like parts of your cache hierarchy. And these are fixed because they're in the machine, they have nothing to do with the data structure. And these lines are the PMA and the B tree sizes. So it's going up as you get more elements in the data structure. The blue line is the PMA, the black line is the B+ tree, and both of them are pretty similar. And one of the main issues is that both of them exceed the size of L3, which is like the last level of your cache hierarchy, between just like 1 million elements and 10 million elements. So 1 million elements is not a huge amount of elements. So like when your data structure gets to be a reasonable size, it's already falling out of L3, which is the reason that PMA searches are so slow. However, the PMA heads, which is the new array that we've co-located the search path into, is much smaller than the total size of the PMA. Like you can see, it's orders of magnitude smaller, and it exceeds the size of L3 when the number of elements is over 100 million, which is much bigger than it used to be. So even this simple trick of just moving the heads into a separate array already allows us to fit into cache when the data structure is much bigger. So the most natural way of storing the leaf heads is the same order that they appeared in the original PMA, and we call this linear order. So I've illustrated the implicit binary search tree that the PMA leaves define, and I just order them. I order the nodes left to right, so like 0, 1, 2, 3, and so on. So linear order just stores the leaf heads in this order, so like 0, 1, 2, and this is great because the number of heads here is already much smaller than the total size of the data structure, like we just saw. However, like you still have to jump around in memory when doing the binary search. So we would start at 7, and suppose we wanted to search something in this subtree, then we would jump to 3 and jump around here. There's another type of ordering called Ettinger order. In the literature, it's also called heap order or in order. And originally, actually, Ettinger order was introduced in the 1500s for a method of storing genealogical trees. And the way that Ettinger order works is that it stores the elements at each level first, and then it stores them from left to right. So like the first level is this top level, and it only has one node, which is 7. So it puts 7 in the front. And the next level of the tree is 3 and 11, so it stores 3 and 11 here. And then the next level after that is 1, 5, 9, 13. So we have 1, 5, 9, 13 here, and then the lowest level is the same idea. And the reason that Ettinger order is good is because when you do a search, you start at the beginning of the array, and the next step in the search is always the next like chunk of memory that you're going to read. So instead of starting in the middle in linear order, now we start at the beginning in Ettinger order. And the next step of the search is either going to be one of these. It's either 3 or 11. So it makes better use of the cache line, and it also makes better use of other things in the machine, like the prefetcher and the branch predictor. And there's another even fancier ordering called B-tree order, which is here. I'm not going to go into detail about it, but it is a blocked version of Ettinger order. Ettinger order is for binary representations. B-tree order is like for arbitrary standout. Yeah, okay, so this is two plots. This is search throughput and insert throughput. So first I'm going to talk about the search throughput one. The y-axis is queries per second, since point queries, up is good, and the x-axis is the number of elements in the data structure. And we expect the number of queries per second to go down as the data structures get more elements because they're going to get bigger, so they have to process more memory. And indeed, that is what we see, like they're all going down. And like expected, the PMA is the worst for point queries because it's asymptotically suboptimal, and also it has to jump around in memory when doing the binary search. The B tree is asymptotically, the B plus tree, I guess, is asymptotically optimal for point queries. And indeed, we see that it is better than the PMA. So like this black line, which is the B tree, is higher than this blue line, which is the PMA. Even the simple optimization of co-locating the leaf heads in SPMA linear, which is yellow line, brings the insertion throughput higher than the B plus tree because it co-locates the leaf heads and it allows them to fit into L3. And using these fancier orderings like Ettinger and B-tree brings the throughput even higher than that because it not only makes use of the cache hierarchy, but it also makes use of things like prefetching. So it even decreases the latency with other things like prefetching and the branch predictor. And here we have insertion throughput. So this method of co-locating the search path by co-locating the leaf heads doesn't explicitly affect the insert in the sense that like we didn't change the insertion algorithm. But the way that insertion works in the PMA is like you do a search to the leaf that you're going to insert the thing into, and then you do some like moving around and you insert the element. So if you speed up the searches, you speed up the inserts because searches are a key part of insert. And yeah, so this y-axis is inserts per second, and the x-axis is the number of elements inserted. And PMA insertions are also suboptimal. So we can see that the traditional PMA has the worst insertion throughput out of all of the options. The B tree has better insert throughput and is asymptotically optimal for inserts when compared to the PMA. And again, we see a similar trend as in the search throughput. SPMA linear is better than the B tree, and SPMA Ettinger and B tree are better for both of them, or better than both the PMA and the B tree. Yeah, and kind of going back to what I was saying in the beginning, we expect PMAs and SPMAs to be better for scans because they're one contiguous chunk of memory. So we tested range queries, which are this operation where you want to apply some function or you want to do some processing on a range of your elements. We tested a bunch of different sizes of the range queries. So range queries have a size, which is like the number of elements that you're going to process. And this y-axis is the queries per second, and we expect the throughput to go down as the size of the queries gets bigger because you have to process more data per query. This x-axis is the size of the query in terms of the number of elements found. And we can see that the PMA is slower for range queries compared to the B tree when the number of expected elements found is about less than 100, like there's this crossover point between 100 and 1,000, which is the point at which the cost of the scan is greater than the cost of the point operation. The B tree is better than the PMA for small queries, but worse for large ones because it's worse for scan. And the SPMAs are better on all sizes because they're good for point operations and they're good for range operations. Yeah, so just to wrap up, the SPMA is better for both point and range operations and overcomes this traditional trade-off in data structures between range and point operations. I mentioned dynamic graphs as an example application, but SPMAs would be good for any application with dynamic data that requires scans. And yeah, and thank you for listening. If you have any questions or you have any applications that you might think an SPMA could help, please don't hesitate to reach out, and my email is here. Thank you.